Okay, problem 848 says hot air at atmospheric pressure and 75 degrees C enters a 10-meter long uninsulated square duct of cross-section 0.15 meters by 0.15 meters that passes through the attic of a house at a rate of 0.2 meters cubed per second. The duct is observed to be nearly isothermal at 70 degrees C. Determine the exit temperature of the air and the rate of heat loss from the duct to the airspace in the attic. All right. So we have some air coming in at 75 degrees C, and it is losing energy to the attic, and the duct is known to have a constant temperature of 70 degrees C. Okay, so even if that duct were infinitely long, the air temperature would only be able to drop down to 70 degrees C. Okay, so because of that reason, if infinitely long would only get us to about 70, we're going to be much shorter than that, and I'm just going to assume, to get my air properties, I'm just going to assume my bulk temperature is not going to be too much different than what it's coming in at. So I'm going to assume the T bulk is going to be roughly about 75 degrees C, okay, just to get me some properties. So if I go now to air properties at 75 degrees C, I know the density 1.014 kilograms per meter cubed. The thermal conductivity, 0.02917 watts per meter Kelvin. The kinematic viscosity, nu, 2.046 times 10 to the minus 5. My Prandtl number is equal to 0.7166. And my CP value, my specific heat, is 1,007.5 joules per kilogram Kelvin. All right. So that's all my givens. Now let's try and start this problem. Of course, it's a fluid flow problem. We should probably calculate what the Reynolds number is. Okay. So in order to do that, we'll have to get some things up front. We'll need our hydraulic diameter, and we'll need our average velocity, because those both go into the Reynolds number. So my average velocity, V average, well, that's just equal to the volumetric flow rate divided by the cross-sectional area. So that's 0.2 divided by 0.15 by 0.15. This gives me an average velocity of 8.889 meters per second. And my hydraulic diameter, d sub h, I need to use hydraulic diameter because I have a non-circular cross-section. And that is just equal to 4 times the cross-sectional area divided by the perimeter. So we have a square, so that happens to be 4 times, well, the area of a square is just the side squared divided by the perimeter of the square. The perimeter of the square is just 4 times one of the lengths of the sides. So now we see that my hydraulic diameter becomes very easy. The 4's cancel, 1s cancels from the top, and I'm left with the hydraulic diameter is just equal to one of the sides of a square. All right. So that is then equal to 0.15, right? One of the sides is 0.15 meters. Now I can calculate my Reynolds number. My Reynolds number is equal to V times my hydraulic diameter divided by nu. So that is equal to 8.889 times 0.15 divided by 2.046 times 10 to the minus 5. And that's equal to 6.52 times 10 to the 4. Well, this value happens to be much greater than 10,000, which means that I have turbulent flow. Okay. Well, after I calculate my Reynolds number, the next step is always, am I going to have any entrance effects, or can I assume fully developed for the entire length? Well, my turbulent entrance length is just equal to approximately 10 times the diameter. So that's 10 times a hydraulic diameter of 0.15. Okay, and that is just 1.5. Well, the entire length of this is 10 meters, so the L is equal to 10 meters. So we're only going, oh, that's only about 15% of the entire length. And I'm going to say we can live with not including that and assuming fully developed the entire time. All right? So now we have a fully developed turbulent flow in a tube. So we have to just select the right Nusselt number correlation. Well, the Dittus-Boelter equation says that the Nusselt number is equal to 0.023 times the Reynolds number to the 0.8 times the Prandtl number to the 0.3. The 0.3 is because we're cooling. Okay, if we were heating up the fluid in the tube, then it would be 0.4. But for cooling, it's going to be 0.3, which is our problem. So we can plug in the numbers to this. We have 0.023. My Reynolds number I got was 6.52 times 10 to the 4. Raise that to the 0.8. Multiply it by the Prandtl number, 0.7166. Raise that to the 0.3. And I will get a Nusselt number of 147.8. Okay, the definition of the Nusselt number, it's a non-dimensional heat transfer coefficient. It's the heat transfer coefficient times the hydraulic diameter divided by K. Okay, so now I can plug in some values. I have 147.8 is equal to H times my hydraulic diameter, 0.15 divided by K, 0.02917. So I can rearrange this and solve for my heat transfer coefficient, and it happens to be 28.74 watts per meter squared Kelvin. Right? So I've got my heat transfer coefficient. This should help me out a bit. The next thing I need to do is I can try and figure out my temperature at my exit, but I need a couple of more things. Well, I need to know what the mass flow rate is, m dot, and that's just equal to the density times the volumetric flow rate. So that is 1.014 times 0.2, or 0.2028 kilograms per second. Okay. I'll also need to calculate what my surface area is. The surface area of this rectangular duct is just going to be 4 times the side times the length, right? The perimeter of the object times the length will give me its surface area. So that's going to be 4 times 0.15 times 10. And that is equal to 6 meters squared. All right? Well, now I go, well, I have a constant surface temperature case. That's my boundary condition for this flow. So I have to remember that my fluid temperature inside the duct is going to approach that temperature in exponential fashion. Okay? So we look up the equation for what the exit temperature would be with a constant surface temperature boundary condition, and it's T at the exit is going to equal whatever that constant surface temperature is minus Ts minus T initial times the exponential of minus H times AS divided by m dot times Cp. This is just equal to 70 minus 75 times the exponential of negative H I solved for, that was 28.74. The surface area I just got, that was 6 meters squared, divided by m dot, 0.2028 times Cp, 1007.5. Okay. Now I can punch that through, and I get an exit temperature of 72.15 degrees C. Okay, so that's my exit temperature. The next part, part B of the problem says, well, what's the heat transfer rate? Well, this is an open system. I know Q dot then is equal to m dot times Cp times the change in the mean temperature from inlet to exit. So T inlet minus T exit. So m dot was 0.2028. Cp is 1007.5. My inlet temperature, that was 75. And my exit, I just solved for 72.15. And now I found my heat transfer rate, 582 watts.